going. So now I've got to go through this definition of interior point one more time, and then we're going to move quite rapidly into the material, reviewing what I've done and going into new ground. A number is called an interior point of a set when not only does it belong to the set, but it belongs with brass knobs on. It's well inside. What do we mean? There exists, it is possible to find is the same as there exists, a positive number delta such that the entire stick that runs from x minus delta to x plus delta, and I call this the stick center x radius delta. That's what I call it, this open interval. Because one day it'll be a disk or a ball or something more interesting in some other kind of space. That entire stick is included in you. Included means subset. Don't confuse included with belongs to. Okay? The stick is a subset of you. It's included in you. That means every blue number belongs to you. You understand? That's what it says, that there exists delta. And I want to point out that the moment any positive number delta has been found for which the blue interval that you see here is a subset of you, any smaller delta would also do the job. Because you'd get a smaller interval, okay? And I gave you a number of important facts, and some important facts I have not yet given you. But here's one. I said that any number that belongs to an open interval will be an interior point of that interval. It actually works for all kinds of open intervals. An open interval that runs from a number A to a number B, that's the hardest of all the cases, and that's the one that I've done with you. We're going to prove that if A and B are any two real numbers, we've actually done this together, so I'm only reviewing this. If A and B are two given real numbers, and if X is any number in the open interval that runs from A to B, in other words, if you assume that A is less than B and that X is a number strictly between A and B, meaning that A is less than X less than B, then X must be an interior point of that interval. When a number is an interior point of a set, the set is called a what? Begins with N. A neighborhood of the number. What does it mean when a set is a neighborhood of a number? It means that the number is an interior point. What does it actually mean? It means there exists delta, not for every. Okay? There exists delta greater than 0 such that the stick center x radius delta is a subset of the given set, whatever you call it, U or Rumpelstiltskin or whatever you call it. So now, I'm going to prove that if X is a number in the open interval that runs from A to B, that's assumed, I'm going to prove that X must be an interior point of that interval. And this is the proof. I'm giving you only a very quick review. We defined delta to be the smaller of the distances from X to A and the distance from X to B. In other words, you look at X minus A and you look at B minus X. And you take the smaller of those and you call that delta. And then you prove that the interval center x radius delta is a subset of the open interval that runs from A to B. This is what we did last time, and I am merely referring you to this fact. You have to go and study it now. Okay? I'm not going through the proof again. I'm simply reminding you that it is here. I know that after a whole week, either you're sitting pretty because you've written this out 20 times in 7 days, or the last time you ever looked at anything like this was when you were last in this room, in which case you are cooking your own goose here. And if you are cooking your own goose, you better not be a vegetarian. Actually, people tell me that goose is very good. I've never tried it. When I've seen it on sale anywhere, it's been helishingly expensive, especially if it's kosher. So anyway, endpoints of an interval are never interior points of the interval. Please don't think that all we're interested in is intervals. But as far as intervals are concerned, points in an interval that are not endpoints are always interior points. And I did it for the case in which the interval runs from A to B. What would you do for the case in which the interval runs from A to infinity? It's the set of all numbers greater than A. And you've got a number x in there. How would you find delta greater than 0? Well, the danger would be that you mustn't go down too far to the left. Isn't that right? To the right, you've got freedom. So how about we define delta to be x minus A. Easier, see? What if the interval was minus infinity comma A? Then you would say, I define delta to be A minus x. You see? The hardest case is where the interval runs from a number A to a number B. If x isn't there, now you've got to take the smaller of B minus x and x minus A. Please go through this proof. Any member of an open interval must be an interior point of that interval. And then I pointed out, I think I pointed out that the set of integers can't have any interior points. Why? If you take any real number and a positive delta, and you go from that number minus delta to that number plus delta, there are a bunch of numbers in there, right? There's no way they can all be integers. You understand? So no number can ever be an interior point of the set of integers. More interesting, if you look at the set of irrational numbers, listen to me. If you take a number and a positive number delta, and you go to the left by delta and to the right by delta, don't you know that there are some rational numbers in there? They can't all be irrational. You understand?
But they're not all rational either, so the set of rational.
Well, there's one thing at a time. Let's do one theorem at a time. You're right, but yes.
So the interior point has to have the same property as the endpoint of the interval?
An interior point must basically smell like a point of an interval that's not an endpoint. It must have that kind of behavior, that there must exist, in order for a number x to be an interior point of a set, it must be possible to find, there must exist a positive number delta, such that the whole of the interval running from x minus delta to x plus delta is a subset of your given set. So if your set was the set of irrational numbers, it would be impossible to find a solid interval that was a subset of that, because any interval is going to have some rational numbers in it as well. And so it can't be a subset of that. And as Julie was trying to say, the same goes if you were working with a set of rational numbers, because in any interval there are also irrational numbers. To be absolutely honest, I haven't even proved to you in this course that there is an irrational number. And you say, well, what about root 2? And I say, well, what about root? I have no idea what that means. If you look at the fundamental properties of the number system, we had a plus and a times and arithmetic and distributive laws and inequalities and supremum. I didn't see a square root there. That needs to be a theorem. Squaring is fine, but square root? Who says? That's going to be a theorem. We might not even reach that theorem in 4381. The proof, when you get to it, is 2 lines, but it's still got to be done. It's 1 line, actually, but it's got to be done still. Anyway, that's why I did it this way rather than the other. Now I'm going to tell you something very simple. Any set that includes means a set includes another set when the other set is a subset of your first set, right? Any set that includes a neighborhood of a number must also be a neighborhood. If you're bigger than a neighborhood, you're a neighborhood. So let me tell you what I mean. To spell this out, we are assuming that U is a neighborhood of X. What does that mean, U is a neighborhood of X? It means there exists delta. By the way, you don't have to use the letter delta. You want to use an R. You can use a
Pink balloon?
a banana, right? So anyway, there exists delta greater than 0 such that the interval center x radius delta is a subset of the given set. Here's a little hint for you. If you ever want to type this interval, if you have bothered to download my fragments, hold down Control and type XD, it will type this. If you want this interval centered at W, WD will do it. If you do XE, it'll make it with an epsilon. Just thought I'd let you know. Okay. We are assuming that U is a neighborhood of X and that U is a subset of V, so that V includes U. Our task is to prove that, let me say this, we want to prove that V must also be a neighborhood. If you have my fragments, NH makes neighborhood. I can't bear to type that word. That V must also be a neighborhood of X. Okay, what must you do to prove that V is a neighborhood? You must prove that something exists. How do you prove that something exists? You bring one in through the door and show it. Okay, this is how we do the proof. Using the fact that, if you want to know how to type that quickly, if you have my fragments, UTFT does it. Using the fact that U is a neighborhood of X, we, what does it mean? U is a neighborhood of X. It means we are given that there exists delta greater. So when something exists, what's the next word? Choose. If you know the language, the proof will begin to write itself for you. Using the fact that U is a neighborhood of X, we choose delta greater than 0 such that the interval center X radius delta is included in U. And we see at once means don't bug me, it's obvious. See? We see at once that this interval is a subset of V. Because if it's a subset of U, it's the fact that U is a subset of V. There you go. See? So I hope you're not going to ask me to prove a theorem that the union of a couple of neighborhoods of a number as a neighborhood is boring. You see? Because if you go take bigger sets, it's automatic. What's much more interesting is making smaller sets. Intersection. So we're going to have here the intersection of two neighborhoods of a number must also be a neighborhood of that number. And we're going to prove this fact. Why did I leave this in? I wrote this when I was working yesterday with Jennifer, and I had no intention of leaving it here. Because I can't point at something I need to write while I'm talking. We assume that U and V are both neighborhoods of X. We want to prove that U intersection V must be a neighborhood of X. Is this clear what our job is? Okay? So now I know that U is a neighborhood of X. What's given? Given that U is a neighborhood of X, what do we know?
Does stick radius delta such that
No, I've got to hear a word here. There exists, right? That's what the definition says. There exists delta. You can't talk about delta until you've introduced that it is possible to find, right? And when something exists, you say choose. That's the next thing you have to say. Choose. Delta. I'm going to call it delta 1. Greater than 0, such that the interval center x, and the only trouble is that this is harder to type because I haven't got a shortcut. The interval center x radius delta 1 is a subset of u. Okay?
Is delta an epsilon?
No, you could, but I think maybe it's kind of nicer to. Come on, you. I don't know what the hell is happening here. Choose. I don't know. It wouldn't drag. Choose delta 2 greater than 0 such that the stick center x with radius delta 2 is a subset of V. Okay? Now what must you do if you want to get an interval that is a subset of the intersection? It's got to be a subset of U, and it's also got to be a subset of V. How do you guarantee that you inside U and you inside V as well? I mean, I'm trying to find a radius of an interval, a positive radius of an interval that will stay inside the intersection. The next word in this proof has got to be defined. I'm going to tell you exactly what I want, but I don't know what I want. Define delta to be, I can go that far, to be what?
The smaller of delta 1 and delta
To
2.
be the smaller of delta 1 and delta, of delta 1 and delta 2, the smaller, right? Look at the picture. In this picture, I happen to make delta 2 smaller. And delta is delta 2. Had it been the other way, if delta 1 had been smaller, delta would have been delta 1. Then the interval running from x minus delta to x plus delta is a subset both of the interval running from x minus delta 1 to x plus delta 1 and a subset of the interval running from x minus delta 2 to x plus delta 2, because delta doesn't exceed either of them. You see? There you are. And observe that the interval center x radius delta is included in U, and it's also included in V, so it's included in the intersection. You see it? So the intersection of two neighborhoods of a number is always a neighborhood of a number. And let's come and do this. And to some extent I'm reviewing last time, but to some extent it's been 7 days. I mean, I don't trust you. You see? Now what if you take the intersection of 3 neighborhoods? 3 neighborhoods called U, V, and W of a given number x. Well, you do this. You say, I'll take the intersection of U with V, that's a neighborhood by this theorem, and then you intersect that neighborhood with W, and you get a neighborhood. What do you have 4? You can do it this way, or you can do it the Spock way, right? See? So, anyway. All my students know about Spock doing this, and hardly any of my students have any idea what Spock had in mind. But but what was it all about? Where did it come from? I'm not telling you, but I'm just issuing that as a challenge. Where did it come from? He was basically making an inside joke, and if you ask me, I'll tell you, but I'm not going to say here because there's no time. So anyway, what if you had 55 neighborhoods? I'm going to give you an alternative proof. If you've got 55 neighborhoods called U1, U2, U3, U4, U5, all the way up to U55, you choose delta 1 greater than 0 such that the interval from x minus delta 1 to x plus delta 1 is included in U1. Now you choose delta 2 greater than 0 such that the interval from x minus delta 2 to x plus delta 2 is included in U2. And then you choose a delta 3 greater than 0 such that the interval from x minus delta 3 to x plus delta 3 is included in U3. And you carry all the way through for each j equals 1, 2, 3, 4, 5, 6 up to 55. You choose delta sub j greater than 0 such that the interval from x minus delta j to x plus delta j is included in uj. Now you've got 55 positive numbers. One of them is smallest. Definition, delta is that smallest. The interval from x minus delta to x plus delta is inside every one of those other intervals, and it's a subset of the intersection. See? That's an alternative proof. My students sometimes prefer doing it sort of by step. The intersection of 4 neighborhoods is always a neighborhood, and you have 5 neighborhoods. Well, then you take the intersection of the first 4, and then you tack on the last one you intersect. You see? Whichever way you like. Okay? What about infinitely many? I'm going to show you in a moment that the intersection of all those intervals is singleton 0. Let me tell you the significance of this example. For every positive integer n, 1 over n is a positive number. Is that not? This is an open interval, is it not? This open interval starts at a negative number. Minus 1 over n is negative, it's less than 0. And 1 over n is positive, is it not? This interval from minus 1 over n to plus 1 over n is a neighborhood of 0. A neighborhood of 0 for every positive integer n. Okay? But if you take the intersection, do you know what is meant by the intersection of all these sets? A number is in the intersection when the number belongs to every one of them, you see? The intersection of all these intervals turns out to be this. How do you read this aloud? Singleton 0. Don't read 0, please. Singleton 0. It's the set whose only member is 0. And what I'm saying to you is that the intersection of all these intervals is singleton 0. Believe that for just a moment, because I can't say more than one thing at a time. Is this a neighborhood of 0? The answer is hell no. There's not a chance. If you take a positive number delta and you go from 0 minus delta to 0 plus delta, you're picking up lots and lots of numbers other than 0, right? Singleton 0 is not a neighborhood of 0. So if you believe me that this intersection is singleton 0, the fact that all of these intervals are neighborhoods of 0 warns us that sometimes you can take infinitely many neighborhoods of a number and take the intersection of them, and lo and behold, you don't get a neighborhood of that number anymore. You see? That's what this is about. It's a warning. Oh yes, the intersection of 55 neighborhoods of a number will be a neighborhood of that number. You can even have 56. You can even have 56 million neighborhoods of a number, but you can't have infinitely many without running into the danger that the intersection might fail to be a neighborhood. Now I need to explain something to you. Given a number p greater than 0, I need to explain why this number p is not in that intersection. Do you understand what I'm saying? I'm trying to tell you that this intersection contains no numbers other than 0. 0 it certainly contains. I hope you know that 0 always belongs to that. Yes? So 0 is in every one of those intervals. So 0 is in the intersection. I want to tell you that a positive number will never belong to that intersection. Okay, well, I need to explain why P doesn't belong. Well, let me tell you what I need. I need to get my hands on a value of n, a positive integer, n, such that P is not in the interval from -1 over n to 1 over n. That P fails to belong to all of them, meaning what? There is at least one of them to which P doesn't belong. Do you understand? I'm going to draw you a picture. Here is the number 0. Oops, doesn't look like a 0. Does that look like a 0? Right. And let's put a bit of number line. And I'll put 1 over n over here. And I'll give you a bit of number line. Let's make it a bit longer, just so it doesn't look the same. And P. If I find a number, a positive integer n, that makes 1 over n less than P, then can P possibly be in the interval from -1 over n to +1 over n? Can it be there? It cannot. So, okay, well, how about, this is how you can get n. Choose an integer n greater than 1 over P. You know you can do that because the set of integers is not bounded above, you see? And observe that 1 over n is less than P. You see? And this makes P not belong to that interval. So given any positive number, you are guaranteed some values of n, actually lots of values of n, for which P is not there, so P can't be in the intersection, because there are some of these intervals to which P fails to belong, so it's not in the intersection. You see? Well, that's all very well for a positive number. What about a negative number? What about... well, I'm not sure if that's what I would say. Now suppose that P is less than 0. I think we need to draw a picture. P is less than 0. There's P. Here's 0. Keep wanting to type a 9. What's the number over here? What's this number over here? No, come on. This is P.
Negative P.
Well, minus P, yes. I would hardly use the word negative to describe something that's positive.
Bad habit.
You see? Yeah, I'll cure you all. That number, that number is positive, is it not? Now, how do you think you're going to find a value of n that makes sure that these guys are not in the interval from -1 over n to +1 over n? This is how you will do it. You know, another way to write this minus P is absolute P. Isn't that right? Might feel more comfortable. And I would suggest to you choose an integer n greater than minus p. Minus p is a positive number. You understand? And observe that p is not in. Yeah. If n is greater than whoops, I meant to put 1 over that, just as I did over here. Where did I do it? Looking for there, just as I did here. You choose an integer greater than 1 over this positive number, and then 1 over n is somewhere in there. And if you go from minus 1 over n to plus 1 over n, you leave out both p and minus p. Do you understand? So I want you to please work on this and see that no numbers can belong to that intersection except for, what's the only number in that intersection? 0. That's what I'm saying. And therefore, there is a danger that the intersection of a bunch of neighborhoods of a given number might sometimes fail to be a neighborhood. But that's when there are infinitely many.
So if there's infinitely many, if an intersection of infinitely many neighborhoods, will it always fail?
Not always. I'm saying there's a danger that it may.
Okay.
What if every neighborhood was the same set U? Then the intersection would be also the same set U.
True.
So, okay. All right, folks. And I could give you better examples. Now I'm going to define what we mean by an open set. So this is now moving forward. Definition of an open set, and I've written it here. We call, you understand that that's a definition word? When you see the word call, we call a set open when every member of the set is, hey, did I do?
What are you looking for?
Yes, but I've got to do something with you and I can't find it here. Did I forget to write it?
What is it?
3, 4. Is there something missing? I will have to add it. It got eaten by the computer. I know I had it here. I had it here yesterday evening. Definition of an open set. A set is called open when every member of the set is an interior point of the set. I'm going to put it in a different way. A set U is open if and only if, trying to make this happen, if and only if U is a neighborhood of every one of its members. That's another way to say it. I'm going to put it yet another way. A set U is open. Well, I think I will make my sentence easier to say the condition for a set U to be open is that, this is easier to read, is that for every x in U, the number x must be an interior point of U. The number x must be an interior point of U. Do you understand? I'm going to say it yet again in looking for a different color. A set U will be open when what? The condition for a set U to be open is that for every number x in U, x must be an interior point of U. What does that mean? Let's spell it out. There exists delta greater than 0 such that this stick is a subset of U. That's going all the way back to first principles and reinventing the wheel. The condition for U to be open says that for every x in U there exists delta greater than 0 such that this interval is a subset of U. You have to be so careful how you write this sentence. For every x in U, once you have made a commitment about which member x of U you are talking about, for that x there exists a delta greater than 0 such that this interval is a subset of U. You can't commit yourself to any delta greater than 0 until after you've said which member x of U you're talking about. That given any member x of U, now that you are looking at a member x of U, for this particular x you can now say there exists delta greater than 0 such that starting at this x and going to the left and to the right by delta, you get an open interval that's a subset of U. Please don't say there exists delta greater than 0 such that for every x this happens. There's not one delta that works for all the x's. So that's the condition for a set to be open. And guess what? We had a theorem today. Every open interval is an open set. Didn't we have a theorem today? A number that belongs to an open interval must always be an interior point of that interval. We had a theorem. Therefore, an open interval is always an open set. Okay? I ran into word processing trouble for this theorem. I wasn't sure how many of you would be savvy enough to be able to copy something in to a folder in your machines. So I'm using an older version of my screen style. You know, my instruction to you to make a document to send me was always to take a lecture notes document and you save as. I never said a book. I never said a document from the textbook, did I? Those are a little bit more sophisticated, and I'm a bit scared if you move them to a new folder that you may have trouble opening them. And anyway, so I had to use this horrible symbol for a curly F. I'm not proud of this. Honestly, I think I better do better. I have to give you all an instruction to do something in your machines. And then what happens if you go and use a school machine? I'll have to ask Ryan Beckett to do this for me. So anyway, in the meantime, I've got this curly F over here. Can you live with it?
Can you do italics?
I want a curlier thing. This, right. I'm using this symbol for a bunch, a family, a collection, a set of sets. We assume that curly F is a family of open sets. And we're going to prove that the union of all these sets, the union of all the sets in the family, must also be open. I'm going to prove to you that if you ever have a collection of open sets, then the union of them all is still open. And did I say that this family had to be finite, only has 55 members or 55 million members? Did you see the words here? Finite? I did not. I mean, any collection can be massively infinite. I don't know anything about it. If you have any collection of open sets and you take the union of them all, you will get an open set. And we're going to prove this. So how do you prove that any set is open? Let's think, folks. What is the statement that a set is open? I've written it several times in different ways. The condition for a set to be open says that every member of the set is an interior, next word, point, next word, of, next word, the, next word, set, right? How do you prove for every? I started the proof. Suppose that X belongs to the union of all those sets. Okay? Now, actually, I think I would like to make this yellow. Okay. Suppose that X belongs to the union of all those sets. It is my job to prove that X is an interior point of that union. You understand? Now, what is it that I know? I always ask myself two questions when I'm trying to solve a math problem. The one question I ask myself is, what do I know and how many ways can I say what I know? The other question I ask myself is, what do I want and how many ways can I say what I want? And if I say what I want in a number of ways and I say what I have in a number of ways, maybe I can bring them together. And maybe I can't. Maybe I won't solve the problem. My batting average is not very high. So every now and then I solve a problem and feel on top of the world and get a paper. And then I think it's never going to happen again. And then suddenly one day it happens. So anyway. Suppose that X belongs to the union of all these sets. What do I know? When a point belongs to the union of a bunch of sets, what do you know? What does it take to belong to the union of a collection of sets?
To be in at least one.
Then, yes, there is at least one to which, so in other words, there exists. So what's the next word in the proof, folks? The next word in the proof's got to be choose. Isn't that right? Choose a member, you, of this family. Oh dear. That's making the nice F. Have to make it this way. Choose a member, you, of that family, such that X belongs to you. Isn't that what we can do? Do you understand? Now I'm going to tell you something. The set U, come on, next line. The set U is a neighborhood of X. Isn't that right? And the union of all the members of the family includes you. It's the union of you and some others. You understand? It's bigger. It includes you. And therefore, the union of all the members of that family is a neighborhood of X. This is the proof. I am assuming that curly F is a family of open sets. And I want to prove that the union of all these sets, I haven't given it a name. You want to give it a name? Rumpelstiltskin. I want to prove that the union is open. What is it that I need to prove? I need to prove that every number in that union is an interior point of the union. Suppose that X belongs to the union. Now, what is it that I know about X? I know that X belongs to at least one member of the family, that there exists a member of the family to which X belongs. Yes? And when something exists, you say, choose. Choose a member of the family to which X belongs. See? Well, this set is a neighborhood of X because it's open and X belongs to it. And the union of all the sets in the family includes you. It's the union of you and some others. You see? And therefore, so we've just proved that every number in the union is an interior point of that union. There it is. Okay? And now, I've said that the union of any collection of open sets will be open. Intersection is much more, you've got to be much more careful about it. The intersection of two open sets will turn out to be open. You can even handle 3 or 4 or 5 or finitely many. I'm just doing 2 for the moment. And let me tell you what we're assuming. We assume that U and V are open, and we want to prove that U intersection V is open. Do you understand what I want? Okay? Okay. What do we need to prove? Here, I'll use this color. We need to prove, I'm just thinking aloud, that every number in this intersection is begins with I. Ice cream. No. Interior point of U intersection V. Did I spell that correctly? Incidentally, to all of you, please be aware that there's a spell checker in Scientific Notebook. You can save yourselves some embarrassment. Sometimes spell checkers increase the embarrassment. I have seen some weird things. An old version of Microsoft Word, did I tell you this? Every time I wrote Lewin, it changed it to Lude. And in the university world, we have what we call research assistantships and teaching assistantships. It's a common word in the university world. And Microsoft Word changed assistantships to assistants with an apostrophe on the S, assistants hips. It's what it gave. These are true. These are actual true things.
I don't feel so bad about it.
Yeah.
And
nevertheless, I recommend that you run the spell checker here. We need to prove, right? We need to prove that every member of that set is an interior point of that set, right? So how do you prove for every? Suppose, right? Suppose what? Suppose that X belongs to that set, right? Well, I want to tell you something. Since X definitely belongs to U, and U is open, isn't U given open? We know that X is an interior point of U. Okay? Blah, blah, blah. X is an interior point of V. Right? Because X is an interior point of U and X is an interior point of V, I will write similarly, we know that X is an interior point of V. If you don't like that, write it out. Say x belongs to V and V is open, so x is an interior point of V. Now look above. Therefore, x is an interior point of U intersection V, because we did it over here. The intersection of two neighborhoods of a number must always be a neighborhood of that number. You see? Now, you don't have to write the proof this way. You know what some of my students prefer to write? They say, I'm going to reinvent the wheel. Using the fact that x is an interior point of U, choose delta 1 greater than 0 such that the stick running from x minus delta 1 to x plus delta 1 is included in U. Using the fact that x belongs to V and V is open, choose delta 2 greater than 0 such that the stick center x radius delta 2 is a subset of V. Next word. Next word. Define delta to be the smaller of delta 1 and delta. If you feel like it, that's a lot of busy work. You're just repeating the other proof. Maybe a good idea, give you practice. Maybe a bad idea, drive you crazy. I don't know, you decide. So, so I didn't forget to do this. I put it in over there. I originally had it further up in the document, that's why I panicked. But it's here. We're going to prove that the set of interior points of a set must be open. And this is what we're going to do. We assume that x is an interior point of a set called S. I actually think that I'm not saying this nicely because I want to prove that the set of interior points of S is open. So I think I better give it a name, otherwise my writing is going to be very cumbersome. So we assume that S is a given set. A given set, and we define U, big U, to be the set of all interior points of S. I'm putting it this way, it is a lot clearer. What I was saying before is quicker. I'm doing it more slowly and I think it's better. We assume that S is a given set and that U is the set of all interior points of S, and our task is to explain why U must be open. Read this. The set of interior points of a set must be open. We are assuming that S is any given set. Is S an interval? Not necessarily. Is S this kind or that kind? Or I know nothing about S. You see? Could be empty even.
But the empty set's open.
The empty set is open. It's worth commenting about that. The empty set is open. Actually, the empty set's a rather boring example of an open interval. But that's perhaps too cowardly to say it that way. When a set fails to be open, you know what you know. Let's say this. A set is called open. Where is it? Where is it? I can't find it. Here. The condition for U to be open is that for every x in U, x is an interior point of U, right? When a set fails to be open, what does that mean? There exists a member of the set that is not an interior point of the set. Isn't that right? Well, then there jolly well has to exist a member of the set, and therefore the set can't be empty. Any set that is not open has to have a member, at least one member, that is not an interior point of the set. And therefore it's got to have at least one member and can't be empty. So the empty set is open. You know what else is open? The entire number line is open. It's actually an open interval. That's perhaps the easiest of all open sets. Take any number, go to the left by 10, and to the right by 10, you've got an interval center. That number, radius 10, is included in the number line. You don't like 10? Try 11. Now let's come and do this. The set of interior points of any set must be open. We assume that S is any set whatsoever. And I'm giving the name U. That's what I wasn't doing at first, and I think I would have made this harder. I'm giving the name U to the set of interior points of S. And I want to explain why U must be open. So I'm going to change color, and let me tell you what it is that I've got to do. I'm trying to just spell out what I need to do. What is my task? I need to explain why for every x in U, reasonable, there must exist delta greater than 0 such that the stick is a subset of U. Isn't that what I've got to do to explain that the set U is open? I've got to prove that every member of U is an interior point of U. So let's now come to the point. How do you prove that something happens for every x in U? Suppose there exists. You suppose that x belongs to U. How do you prove that every member of U eats chocolate? Suppose that x belongs to U. How would you prove? Suppose that every positive number eats brown bread. Suppose that x is a positive number. How do you prove that every chicken, I don't know, has 3 legs, right? Suppose that x is a chicken. That's basically the way you would, if you were doing this in mathematics. Okay. So, suppose that x belongs to U. Now, what is it that I know? I have just supposed, let me just write this here. I know that x is an interior point of S. Do you understand? What was U? Look here. U is the set of what? Interior points of S. S is an interior point of S. Okay. What does it mean, x is an interior point of S? What is given when x is given to be an interior point of S? X is an interior point of a set means what? Spell out the definition. So there exists something. What's the next word? Choose. Choose what? Look here. The statement, x is an interior point of S, that means there exists delta greater than 0 such that the delta stick around x is included in S. And when something exists, you say, choose. Choose delta greater than 0 such that this stick is a subset of S. Okay? What a pity it wasn't a subset of U, but I don't have that. Well, now comes the punchline. Every member of the interval, this interval, is an interior point of that interval, because that's an open interval. This is a fact about open intervals, is it not?
And that intervals.
And the fact that this interval is a subset of S, therefore, tells us that every member of this interval is an interior point of S.
And the interior points of S belong to you.
You see, look here. If a number is an interior point of a certain set and you take a bigger set, isn't your number also an interior point of the bigger set? That was one of the first things I told you. If a certain set is a neighborhood of a number and you take a bigger set, a set that includes it, any set that includes a neighborhood of a given number is also a neighborhood of the number. Yes? If you take any number in that interval is a neighborhood of the number. I didn't want to name it. Call it Y. Call it Charlie. If you take any number Charlie in here, isn't that interval a neighborhood of Charlie? And S includes that interval. How did we choose delta? This interval is a subset of S. So therefore S is also a neighborhood of that Charlie. See? Every number in that interval is an interior point of the interval, and therefore jolly well is an interior point of the bigger set S. This tells us that this interval is included in U. Every member of that interval is an interior point of S. So I have then, look what I said, read this. I need to explain. I need to explain why for every x in U there exists delta greater than 0 such that this interval is a subset of U. Right. Suppose that x belongs to U. Look what I've got. I've got a positive number delta, and this interval is a subset of U. Haven't I finished? Let me go through this argument one more time and then we're going to stop. We are assuming that S is a set about which we know nothing. U is defined to be the set of all interior points of S. We want to prove that U is open. The heading: the set of interior points of a given set must always be open. Okay? Can you close that door for me? Okay. So, I want to prove that the set of interior points of the given set S is open. So I need to prove that for every member x of U, x will be an interior point of U. That's my task. I'm going to spell this out. I need to explain why for every x in U there must exist delta greater than 0. I'm just thinking what interior point means. Must know the definition. I'm working with it. There must exist delta greater than 0 such that this interval is included in U. How do you prove that something happens for every x in U? To prove, suppose, you say, to prove for every, you say, suppose x belongs to U. Now think, what do I know about x? X belongs to U. What was this U? I've forgotten. What is U? Go look at it. What is U? U is the set of what? Of chickens. No, what? U is the set of all interior points. So x is an interior point of S. Now, what does that mean? X is an interior point of S. Think what the definition says. X is an interior point of S. It means there exists, so choose delta greater than 0 for which This stick is a subset of S. Now comes the punchline. Every number in that open interval is an interior point of that open interval, which in turn is a subset of S. When a number is an interior point of a set, it's also an interior point of any bigger set. Earlier seen today, yes? So every number in that interval is an interior point of S. The set of interior points of S was given a name. It was called, go look at it, was called U. Every number in that interval must belong to U. You understand? And so we have in our pocket a positive number delta for which the entire interval that runs from x minus delta to x plus delta is a subset of U, and that's what I said I need to explain the existence of over there. So the set of interior points of any set will always be open. Now I've pushed you a little bit today, but I believe you can do it. Okay? We're going up to, but not including, closed sets. I've put more in the document because it lets you know where we're headed. Okay? That's where we are. Keep your eyes on the contents document, please.